So in first order logic, from propositional logic, we have changed a few things for atomic statements, atomic well formed formulas, and we have added a few new symbols which are there exist and for all, and they are sort of opposite of each other, so we have to add both of them. And we have added a notion of equality of formulas, which is a relation kind of thing. We equality takes two things and then puts a valuation on true or false, but it is special from relations and functions that we have attached with the theory. So starting from the beginning, we in a first order logic we have an alphabet. An alphabet is something which has common things for all first order theories. So each theory would change slightly because we have to give some axioms and give some functions and relations which depend on the theory. So, but the things which are common in every theory is every theory will have some variables, which I'm not sure if they will have to be prescribed beforehand. I think it should be. So it will have some variables which we will write using x, y, z. So we writing a symbol x means we know it's a variable. It's a string for now. We are not defining anything into it. We just know there are some strings which we call variables, and there are some strings which we call logical symbols. There are a few of them only. So there are only we want countably many variables and these many logical symbols, and there is a symbol of equality. There are parentheses, um, our grouping symbols, which we don't really need but we want for our human readability. And we have the quantifiers for all, and they exist. These are symbols which we know when we write them, we know what they mean. And we have a few more strings. We have functions which will supposedly take a few things and give you a new thing, take a few objects and give a new object, and relations which will take a few objects and that will have a truth value or false value. So they are different by definition. Functions can take n things, and n can range from 0 to 1, 0 to any natural number. A zero array function, a function that doesn't take any input, is just a function that gives a constant output. So it will be just like a or something. But it like we have not defined any input and output system yet. So it just strings. We just know when we write a, it's a zero array function. And when we write f, it's a some n array function for some n. We exactly know what n is. We need to know what n is, what is the which kind of function it is. And similarly for relations, relation will take at least one object. We will define what those things are, but for now they are just strings. So we have these few alphabet. um, this is the language. A language would contain um, variables, logical symbols, equality. These are the common in every theory, so we don't have to really learn and every time we are defining a new theory. A theory means piano arithmetic would be a theory. Group, a group with its axioms of a group is another theory. And then we'll discuss what are models of a theory. Now, what we want is to define well formed formulas which will um, we will give some truth value to them and then do some propositional logic to it. So we are building this on top of propositional logic. So we need to have some well formed formula which will behave similarly to propositional logic so that we can use the theorems we have proved before. So before doing well formed formula, we have to define something called terms. A term can be of two types. Variables are terms. X is a term. If I take a two-array function and write fxy, like there are two variables and it takes two variables, and then I write fxy, that would give a new term. This is just a string we are not defining any new material into it apart from being a string. uh, Only the fact that if it's an array function, I have to write n variable n terms next to it. So we are defining in terms of induction. So fxy is a new term. I can call it t1. Then I can define ft1y. So we can define it inductively that a term is a general term would look something like just a variable x or an array function f and t1, t2, and then tn. Unique readability, we have to prove that if I write with them without any bracket or commas, we can really read them, which is true, which is possible. But in general, we will give some bracket and give some commas for human readability. We don't need them for um, really reading them uniquely or something. Um, so these are terms, and terms will make up what are we are going to call well-formed formulas. So atomic well-formed formulas, we will have broken them apart, and then in the sense they are not atomic anymore. Atomic forms are made of terms. So if epsilon 1, epsilon 2 are terms, epsilon 1 equal to epsilon 2 is some well-formed formula. How to distinguish them? We will give well-formed formulas a truth value. We will not give variables a truth value. We will assign variables some object. So let's say x plus 5 is equal to 6 will be some formula, well-formed formula in some arithmetic. And then if I assign the object 1 to the variable x, then that statement would be true, and otherwise it would be false. So for example, x plus 5 is equal to 6 would be a well-formed formula. But x is not a well-formed formula. X is just a term. X plus 5 is just a term, where plus is just a two-array function. And what is 5, what is 6, we will define later actually. They are just, for now they are just strings, let's say. And equal, so this looks like this is a term because I have just used, this is of the form fxy. I can write fxy as xfy if it's a two-array function, which we will write for human readability, and they can be uniquely read also. So this looks like t1 is equal to t2. That is a term. That is a well-formed formula. Another case which can be a well-formed formula is take a relation, which we know it's a relation. Functions and relations are similar in this definition, but we have to distinguish them. So R is a relation. It is a n-array relation, and n is greater than or equal to 1. So it will take n terms, and this is a valid well-formed formula. What this means is something like a less than equal to is a less than is a relation. It will take 5 and 6 and give it a truth value. So we will assign truth values to relations. We will not assign objects to relations like we did for functions. So they are different in what we want to do with them, sort of. Other than that, these are two sort of atomic formulas. Now we want to use for all and there exists. So for all xp is a well-formed formula. If p is a well-formed formula, you have defined beforehand. So things like for all x t1 is equal to t2 is a well-formed formula. So we have the difference between t1 is equal to t2 and for all x t1 is equal to t2 is intuitively clear, but as strings they are definitely different. What we want to do is we'll assign a the intuitive meaning of for all and there exist. We'll assign the strings also them in semantics and syntactics, and that will make the statements like going from here to here. The changes will actually mean something. And similarly, there exists x t1 is equal to t2 will also be a well-formed formula. But again, we can also write for all y, because this is a well-formed formula. I can take any p and attach for all x and write p in a bracket, and then that becomes a well-formed formula. We can also make well-formed formula using previously known objects. We take two well-formed formulae and then combine them using a binary connector or not p. These are also inside there. Now we will define proof, and if some assumptions imply p, then that is if and only if some assumptions like p implies q, that would be same in a meta sense as sigma and p, the set of assumptions sigma along with p would synthetically implying q. It's a proof statement. This is a sequence of proof of this. This is a sequence of proof for q, and that will be the same because we have already proven this in propositional logic. Now